This is the third and last lecture out of chapter 12, which is all about solutions. And this lecture is focusing on colligative properties. So colligative property is any property of a solution that changes as the concentration of the solute changes. So basically, if you start out with some type of solution that's dilute and you make it more and more concentrated by adding more solute, any property that changes in response to that change in concentration is a colligative property. So if you think about maybe dilute Kool-Aid and concentrated Kool-Aid, what are some of the properties that might change with that? The shade of color, the actual color is not changing. It's still absorbed at the same wavelength. But maybe the viscosity a little bit, the density, any of those things are colligative properties. The colligative properties that we're most interested in, that chemists are most interested in, are listed at the bottom of the page here. As you add more solute to a solvent, the vapor pressure goes down, the boiling point goes up, the freezing point goes down, and osmotic pressure, you might be familiar with that from biology, goes up. So we're going to talk about each of them a little bit, and I'm going to give you a little concept of, on a molecular level, why that happens, why these properties change. So let's look at vapor pressure first. If you have a closed container, if you remember, the definition of vapor pressure was the pressure due to the molecules that escape a liquid. So it's the gas molecules that exist over the surface of any liquid. Those gas molecules' collisions are what causes vapor pressure. So as you start adding solute to a solution, it's going to decrease vapor pressure, which means the number of molecules in the gas phase will go down as you add more and more solute. Vapor pressure and boiling point are intimately related. If you missed the correlation between those from chapter 11, pay attention now and try to get it. So here's vapor pressure, okay? And vapor pressure increases as temperature increases, just like you would expect, okay? If you have your beaker here with the liquid in it, if you increase temperature, more and more molecules in that liquid are going to be able to escape into the gas phase, and therefore your vapor pressure will go up. So that's no surprise. Now, what is boiling point? Boiling point is when the vapor pressure, so boiling point is when the vapor pressure equals atmospheric pressure. It's the temperature at which vapor pressure equals atmospheric pressure. So here's atmospheric pressure, 1 atmosphere, okay? Normal pressure around us. And where does that intersect with the vapor pressure curve? At 100 degrees. So obviously this graph is of water because the boiling point, the normal boiling point of water is 100 degrees. So that's the definition of boiling point. So anytime the vapor pressure changes, you have an effect on boiling point also. Back to what I was saying a couple of slides ago. When you dissolve solute into a solvent, vapor pressure goes down. And the molecular explanation for that is you can kind of think of these solute molecules. Now, in order for all these colligative properties to happen, it has to be a high boiling solute that we're talking about, like not a gas or something. High boiling, high molecular weight solute. That's kind of assumed. When you add a solute, these high boiling, higher molecular weight particles are blocking or getting in the way, at least of some of the solvent particles from escaping the liquid phase into the gas phase. And so rather than, for example, having, let's say, 7 gas molecules in this particular space, you might have 4. So the vapor pressure goes down. Raoult's law is the first kind of, you're not going to do that many calculations, and if you will, they'll be very, very simple, but you do need to be familiar with Raoult's law. This is a scientist who discovered that the vapor pressure of a solution, of a mixture, is directly proportional to the mole fraction of the solvent that's present. So obviously vapor pressure is dependent on the solvent. That's where the vapor pressure is coming from. So the more solvent there is, the higher fraction of the solvent, the more pressure, vapor pressure there's going to be. So X is mole fraction. So if the mole fraction of solvent is 1, okay, that means if it's all solvent, okay, if that's equal to 1, then obviously vapor pressure equals the pressure of the vapor pressure of the solvent itself. But let's say we start mixing in a solute. So let's say we mix in a solute until the mole pressure of the solvent, or not mole pressure, the mole fraction of the solvent, let's say is 0.9. So there's 90% solvent, 10% solute. And you can see by looking at the equation, according to Raoult's law, the vapor pressure of the solution will be less than it is of the pure solvent. Here's an example, and this would just be a matter of plugging the values into the right place. So put me on pause, take a minute, see if you can get it. To write Raoult's law for you, just so you can kind of have it in front of you, the vapor pressure of a solution is equal to the mole fraction of the solvent. Now you have to remember the equation for mole fraction times the vapor pressure of the pure solvent. Okay, so mole fraction, just to remind you, is moles of whatever you're talking about, which in this case is the solvent. So that's moles of solvent over total moles. Okay, now you're kind of used to doing mole fraction when we're trying to figure out concentration of the solute. Notice that in Raoult's law, it's a mole fraction of the solvent, not the solute. So plugging in the values, this is the calculation for mole fraction. You have to determine what's the solute and what's the solvent. Pure benzene, that's the solvent. And naphthalene is the solute. Okay, so the mole fraction of the solvent, 9.9. The total moles is 9.9 plus 0.1 solute. So here's the mole fraction. Plugging that into Raoult's law. Okay, torr, that's the pressure of the pure solvent. So it only lowers it by 1 torr, but that's the new vapor pressure. Here is vapor pressure curve showing several different materials. They're all hydrocarbons. Pentane, and that may be hard for you to read, but it's C5H12. Hexane, heptane, octane. They're all hydrocarbons. And it just demonstrates that vapor pressure and boiling point are inversely related. As one goes up, the other goes down. So let's look at it for a minute. Remember that boiling point is defined as the temperature at which vapor pressure equals atmospheric pressure. So where is atmospheric pressure? Well, this y-axis is not in atmospheres, it's in millimeters of mercury. So in those units, atmospheric pressure is 760 millimeters of mercury. So we draw the 760 line all the way across, and for this first curve, here's where it intersects with the vapor pressure curve, and that tells us that the boiling point of this substance is maybe 37. The boiling point of the hexane is pretty close to 70 degrees. And the boiling point of the octane is maybe 98, something like that, degrees. So which one of these do you expect to have a higher, well, which one has the, let me rephrase that, which one has the highest vapor pressure at room temperature? So room temperature is around 25. All right, so which of these has the highest vapor pressure? Okay, pentane has the highest vapor pressure. Okay, all the others are down quite a bit lower. Highest vapor pressure. And what can you say about pentane's boiling point, normal boiling point? It has the lowest normal boiling point. Okay, highest vapor pressure means lowest boiling point. So be able to interpret these graphs and make sure that you know the relationship that vapor pressure and boiling point are inversely related. So because of that relationship, as you dissolve a solute in a solvent, as we just said, the vapor pressure will go down, okay, and therefore the boiling point will go up. Looking at this graph, here's atmospheric pressure, 1 atmosphere, and the solutions A, B, C, D, and E are increasing in solute, okay? So A has the least solute. And what is the boiling point of A? Right here. So the boiling point of solution A is, I don't know, maybe 80.2 degrees. And the boiling point of solution B is perhaps 80.7 degrees. And the boiling point of solution C is perhaps 81.5 degrees. Okay, so you get the gist anyway, hopefully. So as you add more and more solute, the boiling point increases. So what do we know so far about? Vapor pressure goes down, boiling point goes up. So here you are going to be doing calculations with colligative properties, and here's the generic formula we're going to use for boiling point elevation, and in a few minutes we're going to be talking about freezing point depression. So take a minute, jot this down if you want, but it's delta T. That means the change in temperature that you're going to measure with the solution. Notice that it's change. It's not giving you a new boiling point. It's giving you the change from the original boiling point. Little m is molality, moles of solute over kilograms of solvent. They do use molality in these colligative property measurements, boiling point elevation and freezing point depression, because since they're varying temperature, they don't want their value for concentration to vary also. Molal does not change with temperature, so that's a good one to use. K is a constant that will be given to you. It's called boiling point constant. And I is a new concept. I'll talk about in a few more slides, but I is a little bit tricky. You need to listen here. It is called the vant Hoff constant. And it refers to basically the number of solute particles you obtain in solution from one molecule of the solute. So in the only time it's not equal, for all covalent materials, I is 1, always. Okay, so if there are only covalent bonds between two nonmetals, I will be 1, and you can kind of ignore the Van Hoff factor. But for ionic compounds, let's look at sodium chloride. What happens when you dissolve an ionic compound in water? It immediately separates into the individual cations and anions. So for sodium chloride, how many particles do you get for every 1 sodium chloride you dissolve? You get 2. So the Van Hoff factor is 2 for sodium chloride. Calcium nitrate breaks apart into 1 calcium and 2 nitrate ions. That's a total of 3 ion particles, so the Van Hoff factor would be 3 for calcium nitrate. So we'll work with that some more. That's kind of a new concept for you. All right, onward to freezing point. We've talked about vapor pressure, boiling point. Here's freezing point, and then we'll talk about osmosis. We talked about the boiling point being elevated when you dissolve a solute in a solvent. Turns out the freezing point is actually depressed or decreased. So boiling point goes up, freezing point goes down. And it's basically the same type of concept. If you have a pure solvent and you start to remove energy from it, the kinetic energy slows down and the particles can start interacting with each other a bit more. And they will interact to form kind of crystalline structures or solid structures. If you have a solute mixed in, represented by these red particles, they're going to interfere with the intermolecular attractions between solvent molecules, and they're going to kind of prevent this green substance, the solvent, from associating into a frozen crystal. And so it makes it harder and harder to freeze. Therefore, the freezing point goes down. So what's the original boiling point of water? It's 100. If you start adding salt or some other solute to water, boiling point might go up to, no, I'm just going to make that up, 108 degrees. The normal freezing point of water is 0 degrees Celsius. If you start dissolving something in water and try to freeze it, it might freeze instead of at 0, maybe at -10. Okay? So that's basically what they do, why they add salt to ice on the roads to lower the freezing point. Right, so the equation we use to calculate freezing point depression is exactly the same as the equation we use for boiling point elevation. We're calculating a change in temperature, and that is equal to molality of the solution. Now in this case, instead of boiling point constant, this is a freezing point constant. And that's different than the boiling point constant, so be careful. And then, of course, that's times the Van Hoff factor I. So let's look at the type of effects we might see on freezing point, depending on a solution. So if we add quantities of salt, the light purple is adding salt to water, and the darker maroon is adding sugar to water. So if we add the same amount of salt and sugar to 2 separate solutions of water, look what happens to the freezing point. It's normally 0 degrees Celsius. You add a solute. When you add salt, 0.5, is it mole? Yeah, I guess it's 0.5 moles of salt. The freezing point goes down to -2. 0.5 moles of sugar, the freezing point only goes to half that amount. And that trend continues. So if you look at adding 1 mole of salt and sugar, freezing point of salt will go down to almost -4, whereas the freezing point of the sugar solution goes only to -2. So the bottom line is sugar is decreasing the freezing point less than salt is decreasing the freezing point. That all has to do with the Van Hoff factor, this I. Sugar is a covalent molecule. It's made between carbon, hydrogen, and oxygen atoms. They're all nonmetals. They make a covalent molecule. Covalent molecules do not separate into ions when they dissolve. They stay as one whole molecule. So the I value is 1. Sodium chloride, salt, on the other hand, as soon as it dissolves, separates into the sodium cation and the chlorine anion. That's 2 particles, so I for sodium chloride is 2. So you would expect the change in temperature for the ionic compound sodium chloride to be twice as much as it is for sugar. So here's an example. These are pretty easy calculations to do. The formula again, delta T equals molality times the freezing or boiling point constant. This one's asking for freezing point times the vant Hoff factor. I would suggest putting the video on pause, seeing if you can do it yourself. This one might be a little tricky because it's not asking for delta T, it's asking for the freezing point constant, which means you need to rearrange this equation to solve for K. Okay, so that means I have to divide both sides by molality times I. So I can get K by itself. That gives me that K equals change in temperature divided by molality divided by I. Okay, and now I plug in these values and see what I got. All right, so let's see the values that you needed to have plugged in. Here's the rearranged formula to solve for K. We need to know change in temperature. That is an absolute value. Don't worry if you happen to get a negative sign, just take the negative away and use the absolute value of change in temperature. So let's see, original freezing point of pure benzophenone minus the freezing point when urea has been dissolved in it. So the change in temperature is 5.7 degrees Celsius. Okay. And so that gets plugged in for delta T. And now we have to calculate molality. The formula for molality is moles of solute over kilograms of solvent. So let's see, all we know is the grams of the solute that we have. Okay, 1.05 grams of urea. We've got to convert that to moles, because to get molality you need moles of solute on top. So 1.05 grams divided by the molar mass of urea, which they were nice enough to give you. That would give us the moles of urea, divided by kilograms of solvent. So you might want to start a problem by labeling what the solute is and what the solvent is. Okay, so benzophenone is our solvent. And you can tell by the wording of the question. So you want to make sure you're comfortable with that. And of course we need it in kilograms. So 30 grams, convert it to kilograms. There are 1,000 grams in 1 kilogram. Okay, so that means that 30 grams is 0.03 kilograms. So here's our molality, 0.583. So the only thing we need to figure out now is I, the vant Hoff factor. Well, look at the solute for that. The solute is urea, okay? And I know you don't know anything about urea. This problem really should have said that it's a molecule, which implies covalent bonds, or it's covalently bonded, or something. But the bottom line is, if you're given the name of a solute and you don't recognize it, it's some common name like benzene, urea, whatever, that's a covalent compound. Okay, otherwise you'll recognize the naming as ionic, like sodium acetate or potassium chloride. You'll recognize that it's, the other's ionic. So all covalent compounds have an I value of 1. So when we plug all these values in, we get a K value, freezing point constant value, 9.8. Look at the units. Okay, look at the formula. It's delta T over molality times I. So you should have degrees C on top for the units, which we do, okay, and moles per kilogram on the bottom. That's where this is coming from. It's got some funky unit. This problem is really tricky, and I really don't expect you to be able to do it at this point. Go ahead and try it if you feel like challenging yourself. But let me point out a couple things first of all. Always try to identify the solute and the solvent. The fact that they're giving us the freezing point of benzophenone, of pure benzophenone in the beginning, lets me know that it is the solvent. And later on they actually tell you. Let's see, yeah. The solute, it's a mystery solute, but here they give you the molar mass. Okay. And they said, so it must be a covalent compound because they said assume the vant Hoff factor is 1. So you can play with that if you want, but it's really tricky, so I'm going to walk you through it. I'm going to start out, as I always do, by writing the formula I'm going to use and plugging in every value that I've gotten so far. So I don't know what the change in the boiling point is, the change in temperature of the boiling point, but I do know the original boiling point. Now remember, delta T is just the absolute value, no minus signs there. It's just the difference in the boiling point. So I'm going to write this in because I think it'll help. Here's the formula for molality, moles of solute over kilograms of solvent. I actually know kilograms of solvent. The problem says that I have 32 grams of solvent. I'm going to convert that to kilograms by moving the decimal place 3 places to the left. All right, so I have 0.032 kilograms of solvent. Now, I don't know moles of solute right off the top of my head, but the problem gave me the figures I need to be able to calculate it. So moles equals grams divided by grams per mole. In other words, moles equal mass divided by molar mass. In our problem, the mass was 2.5 grams, and the molar mass they gave us was 130 grams per mole. So doing this division will give us the moles of solute we have. And that equals 0.0192 moles of solute. Okay, so now we can go back. I'm getting kind of messy here. All right, so I rewrote the equation, kind of clear up what we have so far. And so this is the molality. So if you take 0.0192 and you divide it by 0.032, you get 0.601. That's the molality. And so this is what our equation is looking like now. Okay, so 0.601 times 9.8, that is 5.89. 5.89 equals 48.1 minus the final boiling point. So rearranging that, our final answer then becomes, the final boiling point would be 48.1 minus 5.89. 42.2 degrees. And this is close enough. All right, so that gets kind of tedious. Onward. All right, the last type of colligative property we're going to talk about in Chapter 12 is osmosis. Here are the book definitions, but I do have a couple pictures on the next couple of slides. It's kind of hard to understand. Basically, if you have two solutions that are in contact with one another through some type of filter or membrane, and one of the solutions is very concentrated, so these represent a lot of solute molecules, and the solution next to it that it's in contact with through a membrane or something is quite dilute, okay? What's going to happen is these two are going to try to equalize their concentrations, okay? So that means that this side needs to become less concentrated, and the less concentrated side needs to become more concentrated. Okay, so that's what osmosis is. Semi-permeable membrane is what's in the middle separating the two solutions. All right, so here's a picture so you can visualize it a little bit better. Here would be this right side of the first tube would represent the concentrated solution, and the left side would be the dilute solution. Now the semi-permeable membrane has pores or little microscopic holes in it that are only large enough to let solvent molecules like water flow through it. Okay, they're not large enough to let solute particle molecules flow through it. So the only way to get the concentrated side more dilute, since the solute molecules can't move back and forth, is to allow the solvent, the small solvent H2O molecules, to start moving into the concentrated side to dilute it. So because of osmosis, what happens is the concentrated side ends up with much more pressure, much more water on its side in an effort to dilute. And the osmotic pressure increases until the concentrations of both sides are equal. Concentrations of both sides are equal. So the difference in the volume of the liquid causes what's called osmotic pressure. And the symbol for that is that kind of pi symbol. The equation for calculating osmotic pressure is similar to boiling point escalation, elevation, and freezing point depression, but a couple of really big key differences. One, instead of molality, little m, like we had in boiling point and freezing point, it's molarity, okay? That's because we're not messing with temperature. Remember, freezing point and boiling point, we're changing temperature, so we need molality. And instead of a freezing point or boiling point constant, it is the ideal gas law constant. Pay attention to the units that we need. And temperature must be in kelvins. Vant Hoff factor is still in there. All right, so here's a simple example of it. All right, so as always, the first thing you want to do is write the formula down for osmotic pressure. Molarity times universal gas constant times temperature in Kelvin times the Vant Hoff. Well, they just told us that Vant Hoff is 1. That's nice. Temperature in Kelvin, you can get that, right? If you have Celsius, you just add 273 to get Kelvin. So 310 Kelvin is what you need. I gave you the value of universal gas constant, which is 0.0821. The problem is asking for molarity, that's our unknown, and the osmotic pressure is 7.65 atmosphere. Go ahead and plug those in and see if you get the right answer, and we'll show you the answer in the next page. All right, so first thing you need to be able to do is rearrange this equation to solve for molarity, and which means you need to isolate the capital M by itself. So the first thing we want to do to rearrange is divide both sides by RTI. That gives us the rearranged formula we need. Molarity is osmotic pressure divided by temperature times gas constant times Vant Hoff factor. So I went and wrote all over. There we go. Yay, the eraser works. Okay. So with that rearranged formula, osmotic pressure, 7.65 atmosphere, 310 Kelvin. This is the gas constant, 0.0821. They told us the Vant Hoff factor is 1. When you plug all that in, you get that the molarity of glucose in water solution you should make for an IV solution is 0.3 molar. Here's another example. Obviously, osmotic pressure is big in biology, so these problems are biology-based. So let's see what we have here. 5.7 milligram sample of a protein. It's dissolved in water, so protein is obviously your solute. To give 1 milliliter, that's the total volume of solution. Calculate the molar mass of the protein. What's molar mass equal to? Molar mass is grams over moles. Okay, so if we're trying to find the molar mass of the solute, we need the grams of the solute, which we have, 5.7. Well, that's milligrams, divided by the moles of the solute. We're also given osmotic pressure and temperature in Celsius. So I would like for you to challenge yourself. Tricky problem. Challenge yourself. See if you can plug what you know into the formula for osmotic pressure and see if you can come up with any type of an answer. And then I'll go over I'll work it out on the next page. There is a lot to think of when solving this problem. You're trying to get molar mass, okay, and that's going to come from molarity. You know osmotic pressure, and it is 6.52 torr. However, you've got to be careful. Pressure has to be in atmosphere. The conversion factor between torr and atmosphere is there are 760 torr in 1 atmosphere. Torr is the same thing as millimeters of mercury. And so in atmosphere, our osmotic pressure is 0.00858 atmosphere. All right, so let's plug that in for osmotic pressure now. Okay. The R value that you need to use so that all the units match is 0.0821. That's liters, atmosphere over mole, Kelvin, just to keep track of our units. Temperature has to be in Kelvin to match that Kelvin. And let's see. So 20 degrees Celsius and 273 means we have 293 Kelvin. There we go. And I is 1, the problem told us. All right, so let's see now what we have for molarity of this solution. I'm going to go ahead and do this calculation. And when I do that calculation, it is, molarity is 0.000369 molar solution. All right, so what is molarity? It's moles of solute over liters of solution. And I want molar mass, which is grams of solute over moles of solute. The problem actually gave us grams of solute, so really all we need is moles of solute. The problem told us that there were 5.7 milligrams of solute, which is equal to 0.0057 grams of solute. So if we go back to our expression for molarity, moles of solute per liters of solution. All right, so I want moles out of this, but I don't need this liter. I need to get rid of that liter. liters of solution. It so turns out that the problem said there was 1 milliliter of solution. 1 milliliter is how many liters? 0.001 liter of solution. So I'm going to just play with my units here. If I have 0.000369 moles per liter, and I multiply it by the liters that I have, 0.00100 liter, guess what, guys? I get moles. And I would get 0.006 zeros. So I'm going to go ahead and put that in scientific notation. 3.69 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the minus 7 moles of solute. And now I can get molar mass. Remember, molar mass is grams over moles of something. I have both grams of the solute, moles of the solute. So if I put them together, I'm going to be able to get molar mass. So that is on the next page. And so my molar mass finally of this protein is 14,092 grams per mole. Wow. So proteins, as all biological macromolecules, are huge. Now, before you freak out, that is a really tough problem. That's a really upper level problem that I normally don't put in my PowerPoints, but this is the type of problem I would expect an A student to be able to do. So if that's your goal, that's probably something you want to work toward. So we're almost done with this lecture, but I just want to make sure that you understand the Vant-Hoff factor, I. So I just want to spend another couple minutes on it. I want you to realize that covalent compounds that are all made of nonmetals stay whole when they dissolve in water. They don't split up because they don't contain ions. So things like sugar, glucose, sucrose, things like that will always have an I equals 1, just one particle per one particle. It's only the ionic compounds, which when they dissolve split up into the cations and anions, that give you the Vant-Hoff factor of greater than 1. So the Vant-Hoff factor for sodium chloride, as I said earlier, is 2. Calcium chloride, I is 3. Methanol, on the other hand, is covalent, so I will equal 1. So if I asked you, for example, let's say I'm putting salt on the icy streets to lower the freezing point of water. So freezing point of water is normally 0 degrees. But I want to lower it to, let's say, minus 10 degrees so that the roads won't freeze so easily, and I'm going to pour salt on. Should I use, this is a typical multiple choice question, should I use sodium chloride or magnesium bromide? Think of the formula. The change in temperature for freezing point depression is equal to molality times freezing point constant times the Vant-Hoff factor. Now, assuming I use the same molality of either salt and the freezing point constant for water is the same, the only power I have to change how much I'm going to lower that freezing point is with the Vant-Hoff factor. You clearly want to use a salt that has the largest I value possible. You get more bang for your buck. And as it turns out, street salt is actually calcium chloride. It's not sodium chloride because calcium chloride separates into 3 ions when it dissolves, 1 calcium and 2 chlorides. So I is 3, and you get more bang for your buck than if you used regular table salt. This would be another type of multiple choice question that I might give you. Arrange the following solutions in order of increasing boiling point. So the concept you need to be aware of is that as the concentration of the solute increases, boiling point should increase, okay? And as I increases, boiling point should increase. So both the concentration and the value for I are going to affect how much the boiling point increases. So what I usually do is I multiply, on this type of problem, I multiply the concentrations by the I factor. So what's the I factor for NaOH? It's 2, because that'll separate into sodium and hydroxide. Polyatomics stay together as one unit. So 0.01 times 2 is, let's go over here with that, 0.02. The second one, multiply 0.01. What is the I vant Hoff factor for iron nitrate? It is actually 4, because I get 1 iron and I get 3 NO3 ions. So 4 times 0.01. So far this one's got the biggest effect. 0.02 times, what's the I factor for this? It's 3. 1 barium and 2 chlorides. Oh, this one's going to win. That gives me a factor of 0.06. And finally, 0.03 times non-electrolyte means covalent. Okay, no, it means no ions. So I is 1. So that's 0.03. So the answer is 0.02 molar barium chloride will have the highest boiling point. Next to last slide, here's a relatively easy one for osmotic pressure. Go ahead and try to work that out yourself. It should be pretty straightforward. That's just a matter of plugging in your values, calculating osmotic pressure, and being able to determine what the I is. Sodium phosphate, you need to be able to draw these dissociation of ionic compounds in water, so you end up with subscripts become coefficients. You have 3 sodium ions that are formed from that and 1 PO4 ion. Polyatomics remain intact. So you have 3 plus 1 or 4 ions. That's the I value. Okay, so that goes in for I. Make sure you change your temperature to Kelvin by adding 273 to it, 293 Kelvin, R value, and molarity, which they gave you. Okay, so your final osmotic pressure is 9.6 atmospheres. That's the last slide. We are done with Chapter 12. Don't forget to take the quiz that goes along with this. And your first unit test is coming up. It's going to cover everything in chapters 11 and 12.